All right, so we're going to start the second page of the practice exam 3. And so on this page, we're finding the sum of particular series. And so what we would like to do is look at each one of the series that we're given, try to relate it to a Maclaurin or Taylor series that we're familiar with, and then use that to get the sum of the series, because we can then relate it to a particular function, and then this is just a function value. So for the first part, what we're going to do is realize that this is really just this Maclaurin series, x to the power n divided by n factorial. N goes from 0 to infinity. And of course, this is the Maclaurin series for e to the power x. And so I'm thinking about this value of -1 that I see here as the particular value of x that I substitute into this expression, right? So I want to think about this Maclaurin series for e to the x, and then this sum of this series will take the value when I substitute for x is equal to -1. And so, I mean, it's really just that simple once you make that identification. Now, the sum of this series is just equal to e to the power -1, which is, of course, just 1 over e, right? And that's the sum of our series. Okay, the next one is just written in a slightly inconvenient format. And so what we're going to do is combine these two terms, because we see that we have power n on both of these terms. So we'll combine them, and then we'll ask ourselves if that looks like anything we're familiar with, right? So I have a -1 to the power n. I have a 1/3 to the power n. I can combine those, and it'll look like this, -1/3 to the power n. And of course, this is just an example of our geometric series evaluated at x is equal to -1/3. Right, and so we know that this series is convergent for all values of x between -1 and 1, exclusive, and so the -1/3 is certainly between -1 and 1, no issue with endpoints or anything. So all I have to do is plug in this value -1/3 into this expression, and I get the sum of my series. So -1/3 to the power n from n equals 0 to infinity. This is just equal to the value 1 over 1 minus -1/3. But this is, of course, just 1 over 1 plus 1/3. This is 1 over 4 over 3. And this is just equal to 3 over 4. Okay, so that's the sum of that second series. Now, the third series is a little more complicated, but honestly, the identifying features are the power 2 to the n, or 2n. So I have a power 2n, power 2n. I have this alternating portion, and I have this 2n factorial. And so I'll rewrite this just in a slightly different format. And so what I'm going to do is pull the -1 to the power n to the front of the coefficients. And then I'll look at this pi over 3. Since there's the same power on both the pi and the 3, I can just combine them as pi over 3 to the power 2n. And then I'm dividing by 2n factorial. And then that should look familiar to you. This should look like the Maclaurin series for cosine. So we got n equals 0 to infinity, -1 to the n, x to the power 2n divided by 2n factorial. This is our Maclaurin series for cosine of x. And so we actually know that this is convergent for all values of x. Okay, pi over 3 is certainly a real number, so this series will converge for this value, and more particularly, it will converge to cosine of pi over 3. So we're thinking of substituting x equals pi over 3 into this expression. And so now we have our series, n equals 0 to infinity, -1 to the n, pi to the 2n over 3 to the 2n, 2n factorial. This is just equal to cosine of pi over 3, but cosine of pi over 3 is just equal to 1/2. So this is the sum of the third series. Okay, and that concludes the second problem, and so we'll go to the third problem next.